So today we have Fedor from Moscow telling us something about polynomial dependencies in hypergraph Turan problems.
Okay. So I would like to thank organizers for this opportunity to give the talk. And I would like to discuss my joint work with Andrei, and Lisa, and two our colleagues who are absent here for some reason. But before I will discuss hypergraph Turan-type problems in general, I would like to focus on some particular problem. So let me consider the following structure. We have S sets, and I say that they form a sunflower with S petals if any two sets intersect by the common intersection of all sets. So basically I have some set which I will call a core, the core of a sunflower, and S disjoint petals. This is F1, this is F2, and this one is F3. Well, basically the core can be empty, so S matching is also an S sunflower, but it could be non-empty, like this example. And Duke-Erdős in 1977 asked the following question. So let F be a family from n choose k, and F doesn't contain a sunflower with S petals and the core of size exactly t minus 1. And what is the maximal size of the family F? So to answer this question, at least particularly, can we define the following function? Phi of S and T is the maximum T uniform family that doesn't contain a sunflower with S petals. So without restriction on the core of its sunflower, on these sunflowers. And using this function, Franklin Furedi showed the following. So let k be at least 2 times t plus 1, as t fixed, k also fixed, and n tends to infinity. Then, asymptotically, we have the following inequality. The size of f is at most phi s of st plus something small tending to 0 times n choose chi minus t. Okay, this is an upper bound. We have some function phi, but could we say something else about f? In particular, is this bound type? So Franklin Furedi in this paper showed that their bound is asymptotically tight, and the example is quite simple. We choose a family for which we have this maximum. So a family T that doesn't contain a sunflower with the S petals, T uniform, and T has size, let me denote it by T star, has size exactly phi s t. Okay? Then I will choose n large enough, place T star somewhere on the ground set, there, and construct an example just requiring my sets from S intersect the support of T star only by sets from T star. So T1 from the picture belongs to T star and joined from any K minus T subset outside the support form a set from my example. So formally it can be stated like that. And a simple exercise is to show that this family F indeed avoids sunflower with S petals and the core of size at most T minus 1, but in particular exactly T minus 1. So if F1 Fs from F form a sunflower with S petals and the core of size T minus 1, then F1 intersected by the support of T star form a sunflower with S petals and the core of size at most T minus 1. But these guys, by the definition of T star of F, should belong to T star. I've chosen T to be a family without sunflowers of size S and the core at most T minus 1, but I mean, it doesn't matter because we have uniformity T. So we get a contradiction. And the size of F in this particular example can be bounded like phi T, the size of T star, times the number of sets so outside of size K minus T, outside the support of T star, so it will be, it can be lower bounded by n minus some upper bound on the support, choose K minus T. So, okay, I mean, we have upper and lower bounds that both are defined by some function phi of S and T. And is there other connections between the problem of defining phi S T and the Duke-Erdős problem? It turns out that this connection indeed exists, and we can say more about extremal examples. So in particular, F can be almost fully covered, so up to some remainder, which is 1 over n fraction of all sets of F calligraphic, by some family T that that consists of sets of size T and doesn't contain a sunflower with S petals. So in particular, it doesn't contain a sunflower with S petals and the core size at most T minus 1. So it's not only about the defining, the function phi S T. It's also about extreme families of this problem. So one could reduce the Duke-Erdős problem in some sense to the extremal problem that basically Erdős sunflower problem I will discuss later a bit, but it is a particular instance of another extremal set theory problem independent of K and N. So you have only two parameters here, T and S. Okay. But probably we could say even more than that. We can. So if we impose additional requirements on K, so now k is quadratic in T, we can prove that extremal example from Furedi and Frankel's paper is contained in extremal family F. We can prove even more that if F from our extremal family intersect some, so the support of T, where T is a family which covers our family F, then we either has this set belonging to T, or F intersected by the support of T has size at least T plus 1. So the Furedi's example, Furedi's and Frankel example form a first level of the extremal family, but probably there are some other sets inside F, inside extremal F, which intersect the support of T by more than T elements, T plus 1, T plus 2, etc. And it is indeed the case. Sorry. But let me point out the following. These results can be obtained even we know a little about this function Pst. We know some bounds. I'm sure you know the recent, not very recent, result of advice Italian, its refinements that bounds Pst above. And we almost nothing know about the extremal families T participating in this definition. So we know it for some particular T equals 2, and I'm not sure we know something about T equals 3, but in full generality, we can say almost nothing about these families. But we can obtain all these results. So I would like to say that we obtained not a solution of Duke-Erdős problem, but its reduction to Erdős-Sunflower problem. The problem of determining Pst. So finding largest family T that doesn't contain the sunflower with S capitals. And from the paper of Erdős and Rada, we know that T is at least, extremal T is at least S minus 1 to power T, and at most, so as guaranteed by Weiss and some refinements due to Bell, Warning, etc., that T is at most C log T times to the power T. In the power T. Okay. But this problem gives us not exact results, but some first level approximations. Could we go further and find some problem that determine the structure of extremal family exactly? Well, such problem exists. It could be described by some algorithm, and this problem has size depending only on S and T, such that it fully determines the structure of extremal family F in the Duke-Erdős problem. This problem is different from Erdős-Rada sunflower problem, but it has some nice properties, namely extremal family F doesn't contain a sunflower with the core of size at most T minus 1. So the solution in the Duke-Erdős problem is the same, well, under quite restrictive guarantee requirements on N and K, as for the problem where we forbid a sunflower with the core of size at most T minus 1. So T minus 2 sunflower is also forbidden in T minus 3, and sunflower with the core of size 0, so matching is also forbidden, etc. And this problem is downclosed, is monotone in some sense. Because you forbid a downclosed family of configuration instead of one single configuration where we have the core exactly t minus 1. So let me summarize the discussed properties of the extremal family. If we forbid a sunflower with the core of size t minus 1, then the extremal family doesn't contain a sunflower of size at most t minus 1 with the core of size at most t minus 1, and can be determined by a problem that is independent of n and k. So it's enough to solve some problem dependent on s and t only. And since we know almost nothing about the Erdős sunflower problem, it's natural to conjecture that this is a general phenomenon. We can generalize it to other hypergraph Turan-type problems, and this is indeed the case. The simplest example of this type reductions is the Erdős-Sós problem, when we forbid a sunflower of the size 2. So we just exclude two sets that that are intersected by t minus 1 elements. So I will discuss this problem in more details in what follows with more results and comparing it with previous papers. But in our result with Andrei, we showed that if n is at most polynomial of t times k, and k is at most polynomial, at least polynomial of t, then f is just a trivial intersection family. So we take all sets of n choose k that contain some t of size t. The interesting feature of these results is that to obtain it, we need to strengthen condition on the k. The famous result of Frankel and Furedi tells us that this type of result can be guaranteed when n is some function, n is at least some function of k, and k is at least 2t minus 1. But if we allow k to be polynomial in t, we can get the same result, relaxing our assumption on it. So, okay, it's nice to notice, and this phenomenon is also very general. So there are different regimes, then we can obtain extremal results on in hypergraph Turan-type problems. And these regimes are not fully comparable. Okay. Other particular instance of hypergraph Turan-type problem that follow phenomena we discussed for sunflower Duke-Erdős sunflower problem is the problem of forbidden hypergraph extension. So if we have some hypergraph H with S edges, how large could be the family F such that F doesn't contain an extension of this hypergraph. So we cannot add some pairwise disjoint edges sets to each edge of H. that do not intersect the support of H, obtaining a configuration F that is isomorphic to this one. Okay, so when you add pairwise disjoint sets to edges of H that do not intersect the support of H, this operation is called extension. So we forbid a configuration on S sets that doesn't isomorphic to some extension of H. And what could we say about extremal families? As in the case of Duke-Erdős problem, we cannot hope to say something simple about F, so it is a trivial T intersection or something else, but we could guarantee that an extremal family F doesn't contain a trace of the hypergraph H. So what is the trace of hypergraph? We consider all edges of H and then intersect it by all possible sets V, and then obtain some hypergraph H just by restricting its edges to this set V. And our theorem guarantees that the extremal family F doesn't contain an extension from the trace of H. So it's again a kind of down-closed forbidden configurations, as in the case for sunflowers. Okay. We could even say something more about the size of F using a function which is determined by our hypergraph only, without any reference to n and k. So let me define a function phi of H as the maximum T uniform family that doesn't contain an extension from the trace of H. Then almost all sets from the extremal family F can be covered by such T calligraphy. And in particular, we have F is at most 1 plus square root something poly st k divided by n, not square, cubic root, times phi of H, and minus T choose K minus T, and this result is tight as for the Duke-Erdős sunflower problem. But of course, we can define some extremal set theory problem that is different from maximizing families that doesn't contain an extension of trace of H, that still determine the structure of extremal families, like completely, without any second order approximations. Okay. Another example. So I just would like to highlight that these observations are general for hypergraph Turan-type properties, and except Erdős-Sós forbidden intersection problem or hypergraph extension problem, it can be generalized further. And for example, consider the TS simplex problem. This is a problem that generalizes Erdős-Sós simplex conjecture, but for the case t minus 1, it's Erdős-Sós simplex conjecture, but for arbitrary t, this problem is due to Franklin theory. We forbid structures like that. We have some core of size t minus 1, and then we have a kind of simplex on it. So F1 is union of the core t minus 1 and some edge from the simplex. So when I say simplex, I mean that if so any intersection of over a set S subset of S plus 1 has size at least 1, so it's simplex without core t minus 1, and the whole intersection of this family, so S is a proper subset.
At least one.
At least one. Sorry, at least one. And the intersection of all families is 0. And for general T, I know results of Franklin theory, and people are mostly consider the case T equals 1 and gained a lot of progress in this direction. So I think we know Kevin Lifshitz Hund approximation method, where they require only n is at least some in n0 of S. And, these bounds are tight. Or Curie result, which requires n to be just roughly 2 times k. So the Erdős simplex conjecture is still partially open, but there is a lot of progress. For general T, it is not the case. And we prove the following. So if F doesn't contain an ST simplex, then F can be, and F in extremal, then F can be represented as this family. So all its sets contain some fixed set T of size exactly T. And what I would like to highlight that F is not just T intersection trivially, but it is S-wise T intersection, and so I mean forbidden. So the answer is as we would require all intersections to have size at least T. And okay, why this is important? Is this important? Because this property is a down closed version of the initial property of forbidden configuration like ST simplex. And that's a proper generalization of what we saw previously when we forbid trace of hypergraph in the hypergraph extension problem, or require families to be T intersection in the Erdős-Sós forbidden intersection problem. And okay, so when we write like n is larger than some polynomial function times k, and k is a polynomial some function of st, we would like to figure out what are these parameters that we should place here. So what is S for a general Turan-type hypergraph problem? Or what is T for a general hypergraph Turan-type problem? And when the extremal example can be obtained by forbidding some down-closed family of configuration instead of initial one. And each of the above problem has essentially three parameters. So the size of forbidden configuration S, it is S if for sunflower problem, and the number of edges in hypergraph for hypergraph extension forbidden problem. Okay, the second parameter is T, which defines the uniformity of low dimensional extremal problem that defines the extremal example, so this in particular. And there is some other parameter which we could name a complexity of making forbidden configurations down close. So it is the most rough definition, and I think I should explain it. When I said that the extremal family is so avoid some down close family of forbidden configurations, that can be done assuming K is larger than something. Okay. Just poly ST in this case, or 2T plus 1 in the case of Furedi theorem, Furedi and Frankel theorem. So here it has T plus 1. And how these bounds could be understood. And the answer that we need some internal mechanism inside of the proof that makes the problem down closed or monotone. And this mechanism impose some assumptions on K. So making a problem down closed, so making forbidden configuration family down closed, is almost equivalent of finding some structure in the shadow of F. In most of large techniques for obtaining results in Turan-type hypergraph problems. So we will discuss it more in what follows, but this parameter is essential. And using it, so if we obtain somehow a family of forbidden configurations given initial forbidden configuration, we could define the first level uniformity T just from this family. And T is such number that a sunflower with the core of size L is at most T minus 1 belongs to the family of forbidden configurations. So here is a table with down-closed family of forbidden configurations and the complexity to obtain them. I mean, I understand that complexity term is still not strictly defined, but I hope this is okay. So for sunflower with the T, the core of size exactly T minus 1, the extremal family will avoid sunflowers with the core of size at most T minus 1. And for extensions
of a hypergraph H, the extremal family will avoid extensions of its trace. And from ST simplex, the extremal family will avoid S plus Y. Will avoid S plus 1 Y's intersection of size at most T minus 1. So it means that extremal families will be S plus 1 Y's intersection. And complexity of of making configurations down closed is for this problem T minus 1. How it can be understood? If we have a sunflower of size L, where L is at most T minus 1, we could add some set of size at most T minus 1 minus L to obtain a forbidden configuration, namely a sunflower with the core of size exactly T minus 1. Similarly, for the extension of H, we could...
You mean adding this to all the sets?
All these sets, yeah. Adding this to all these sets. Similarly, for the extension of H, if we have some extension, some hypergraph from the trace, we could choose a set of size S times the uniformity of edges from the initial hypergraph and choose some sets from it such that adding the first set from
maybe intersecting also, right?
Huh?
They can be intersecting.
They can be intersecting, sure. Such that adding the first set to the first set from the first edge from some of a hypergraph from the trace, and adding the second edge to the second set to the edge from our hypergraph from the trace, and the third edge to the third edge, etc. We will obtain a configuration which is isomorphic or is an extension of the initial graph H. And the complexity is the size of this set. Similarly, for ST simplex, one can check that the complexity of so if you have S plus 1 Y's intersections of size at most T minus 1, then you can add a set of size S plus T and add subsets of this set to the edges, so to the configuration of that forms S plus Y intersection of size at most T minus 1, such that the resulting configuration will be ST simplex. And the new question arises. Okay, given these three parameters, could we obtain extremal set theory results for them given n and k additionally? So we have f from n choose k that forbids a configuration such that it has size S, and the complexity of making this monotone is M, and the downclosed family of configurations contains sunflowers with the core of size at least T minus 1. When could we say something about the size of extremal family S. And this, of course, depends on the relations between all these parameters. And essentially, there are a lot of regimes when you can obtain some results using different techniques. So if k is small, very small, then you can apply delta system method, and assuming n is larger than s in the power of polynomial of t and m, so for classical delta systems you will have 2 to the power of polynomial t and m, but it seems that this bound is correct due to recent result of Janser, Sudakov, and I forget Fedor, sorry. So you can obtain first level structural results. You can prove that F is covered by some family T, which is an extremal family in some problem that depends on T, M, and S only. Then you can consider larger K, and moving up, you can relax conditions on N. And instead of polynomial degree here, you get some linear degree. Then you move forward, and if N is polynomial S and T M, and K is polynomial S of S and T and M, you can obtain some results using the spread lemma, so using the spread approximation technique due to Andrei and Dima. But it becomes suboptimal, then K is at least some exponent to the power of polynomial of S and T and M. Then you can combine some ideas of Andrei and hypercontractivity ideas of Kivash, Lifshitz, Keller, Mintzer, and Alon, and other Boolean analysis people, and get the result. Then N is linear in K, and I think this is the best you can hope to obtain. I mean, in general, but in some cases you can move forward and obtain results. Then K is something like 1/2 minus epsilon of N. We will discuss it later. And if K is large enough and N is large enough, you can hope to obtain exact structural results. So prove that the extremal family is determined by some extremal set theory problem independent of N and K, which depends only on S, T, and M. In some cases, so for hypergraphs, it is also determined by the uniformity of the hypergraph, but it can be encoded into M. So there are a lot of regimes, and you should use a lot of different techniques to prove these results. Either approximate, so proof Furedi and Frankel results with the first level approximations, or exact. So let us, for example, return to the Erdős-Sós forbidden intersection problem. It is known that extremal examples are defined by the Frankel families when n is larger than n0 of t and epsilon, and k is 1/2 minus epsilon times n. Due to Frankel and Furedi for large n and k is much smaller than n, and Ellis, Lifshitz, and Keller when k is approaching to n divided by 2. So there are more regimes, then you can analyze this problem. And for example, if n is a polynomial of t times k, and k is some polynomial of t, then you have the same result, but the maximum in Frankel families is attained for trivial t-intersection family. Okay, if n is larger than some exponent to the power of t squared log n, and k is larger than t squared, you again can obtain this result. And if k is roughly around, not roughly, is around 2 times t, then you can apply the delta system techniques and again obtain this result. So there are a lot of different regimes, and they
Let's combine delta systems with this technique.
okay, you can combine, if you impose k is less than ct squared, then you can obtain, this.
Yeah, I just commented this.
Okay, yeah. You can
Delta systems give something else.
something else. It's not that it doesn't give the linear bound, but analyze this guy erasing this condition and assuming n is larger than 0 of t. Okay, similarly for the Duke-Erdős problem, you could obtain different regimes and solve it with assuming some different conditions of n and k. So if, for example, we could prove first level approximation of an extremal family if n is larger than polynomial of s and t times k, and k is larger than polynomial of s and t. Or we can prove this result for n being linear on k, n larger than st to some power linear on t, and k is larger than some constant times t. Or we can prove the same results assuming n is larger than n0 of t, and k is larger than 2 times t plus 1. And as I discussed before, all these regimes require different analysis. Almost different. They combine some ideas from each other, and but however, such results can be obtained. Okay. Well, when I said that there exists some extremal set theory problem that determine the structure of extremal families in the Duke-Erdős forbidden sunflower problem, it is impractical because I didn't provide this extremal set theory problem, a low-dimensional extremal set theory problem that allows us to solve Duke-Erdős problem, but you can move upwards of approximations like not only approximate the first level, but approximate this, the second level, etc. And for small t, it this like t equals 2. This hierarchy become rigid, and you can obtain the exact result, like considering not only only some few first layers of your problems, not the full low-dimensional problem that determine the extremal set theory, the extremal family in the Duke-Erdős forbidden intersection problem. Okay, and let me briefly discuss the proof idea. It follows, almost always, but with some exceptions, the decomposition of initial family into some pseudo-random parts, like uncapturable in Denur and Friedwood analysis of T-intersection family, or spreadness like in Alvai's paper, or homogeneity like in the paper of Andrei and Dean. But there are other notions that can be used here, and they are used, and they also are helpful in some regions, depending on the relations between Turan-type problem parameters. So, roughly speaking, you find some set S1 such that restricting on this set, your family is pseudo-random. Then you remove all sets containing S1 and S1, and find another pseudo-random restriction and proceed like this, and stop when you have a small remainder and a family F, a family of families of pseudo-random families encoded by some family as calligraphic, restrictions that you need to apply to obtain a pseudo-random family in your procedure. And then you work with this S-calligraphic family using the fact that usually S1, S2, S3, S5, etc. has have a small uniformity compared to K. Okay, I have some time. So you wish to prove that the family S that encodes this pseudo-random structure satisfies some conditions, like it is T-intersecting if F is if F forbids intersection by exactly T minus 1 elements. And the idea is as follows: you consider some some sets, like some S sets, and wish to prove that they form they could not form a forbidden configuration or configuration from downclosed family of forbidden configurations. So, and the idea is to use this informal lemma, but it can be obtained for different notions of pseudo-randomness. You prove that pseudo-random families cross-contain a matching. I mean, you can choose disjoint sets in these pseudo-random families such that attaching them to sets from S calligraphic, you will get a forbidden configuration, assuming that so S3, S5, and S4 on the picture form a forbidden configuration. Okay, and it works, but if you would like to prove something more, like in this case, for example, you wish to prove that S calligraphic doesn't contain a sunflower with the core of size at most T-1, while the whole family doesn't contain sunflower with the core exactly T-1. Then you could use some other properties of homogeneous families in general, but it can be also applied to other notions of pseudo-randomness, and find something nice in the shadow of your family F, such that attaching this configuration found in the shadow to the configuration in families in the family S calligraphic, you will form a forbidden configuration, and then you extend it, you obtain a matching in pseudo-random families and get a forbidden configuration in the initial family F. So that allows to prove that S doesn't contain some downclosed, or I mean something more than just initial forbidden configuration. And then you can do something like simplification argument, something, some procedure that makes your uniformity even smaller than before, and prove the desired results. So F can be covered almost completely by T uniform family. Okay, and probably
It's a good point.
point to stop here. Yeah, I think I should stop here and ask your questions if they have them.
Any question?
Maybe one thing you could have drawn also, maybe you can show it, is why this like connection between, let's say, the forbidden sunflower and all these traces and extensions, and this kind of just show that sunflower is an extension of just copies of a bunch of sets. Let's say you had this
Sunflower is an extension of
like the connection between Duke-Erdős problem and this general hypergraph extension, let's say,
Yeah,
problem.
Yeah, I just would to highlight that if H is a multi-hypergraph consisting of the same edges of size t minus 1, then extension of H forbids
Forbidding extension of H is
forbidden extension of H is equivalent to forbidden sunflower with S petals and the core of size exactly t minus 1.
But does he also work for the symmetric group? If you if,
yeah, this is something Fedor probably didn't manage to
cover. It a general phenomenon. So the spread lemma is a particular instance of the measure boosting argument, and you can do something else. But the spread lemma is enough for the symmetric group. But in other cases, you can apply something more. So, for example, there is a result of Lisa, Gosha, Sokolov, and Kolya Terehov for family of codes. And the idea is just apply apply measure boosting algorithm using some semigroups inside, so that form from m to the power n something else iteratively, boosting the measure of f inside a new domain, new domains.
But yeah, after all, you kind of, well, at least for the symmetric group, the way you can see it is you still embed it inside to the end.
Yeah, and there is a very simple way to, like the spread lemma is a way to boost the measure inside the Boolean cube. But in some cases, you should do something more.
what about the more general? You have an abstract group G, and you define intersection by the number of fixed points of G inverse times H for two elements in your subsets.
G
Inverse, little h,
H.
in your family, in your subset of a group G. So you require the number, you define the intersection size by the number of fixed points of pairwise.
Okay. Fixed points.
In some scenarios, it's possible, but
So you say for the symmetric group, you can define it like this, right? Then you can replace symmetric group by any group G. Then
so for the spread method, you need a certain any group can be embedded in the symmetric group, but you need a certain growth rate, let's say. So for spread method, at least you need like symmetric is like n to the n, and you need something like log n to the n at least for this thing to work.
But I mean, for a Q, I think you can do something like that. I bring you group. You can do something like okay. No,
So it is complicated.
it's
yes.
complicated.
So
yeah.
people studied like the point is that many of these things were studied algebraically, right? People try to study them algebraically, but it's extremely hard to get anything, even just Erdős-Sós. So people like Karen Marr and Chris Gottsel, etc. They could study some relatively sparse groups. If you're lucky and you have some kind of Hoffman bound which matches what you want, then you can get something. But it's a very limited set of scenarios. So in that sense, this quasi-random approach is much more robust and much better in that sense. But if you don't have a Hoffman bound and the group is not growing, let's say, fast enough, then I guess it's unclear what to do still. Or actually, in some cases, it's unclear if it's true. The Erdős-Sós, let's say.
Okay, any other questions?
I want to know, you mean the domain can be embedded into the Boolean cube or the biased Boolean cube?
It can be embedded to the biased Boolean cube. So if you can proceed like, for example, for the symmetric Boolean cube, it's enough to embed f to like n squared.
Group, you mean?
Yeah, for the subfamily of the symmetric group, it's enough to embed it into n squared, choose n, and this can be embedded into 1 over n
of 2 to the n squared.
2 to the n squared, for example. But you definitely could embed it into the, in general, not on the symmetric group, but something else. If you are lucky enough, you can embed it into the p-biased Boolean cube, and it will be useful because you can use a measure boosting argument for the Boolean cube, and it works. But it depends on the domain.
Yeah, so this spread lem is very good in that sense because you don't care about the initial measure. You know very little about the initial measure, and then this kind of, but for hypercontractivity things you do care about the initial measure. It can be very small, but not extremely small. Like it can be exponentially small, but it cannot be like super exponentially small or something like that.
So you should assume like.
So not every embedding would work.
It's roughly n minus polynomial STM depending on the problem. So you should assume that any pseudo-random part has size at least.
So in that sense, maybe you can mention this n choose k, ni choose ki thing. That is to give an example that's straightforward. Let's say measure boosting doesn't work.
It doesn't work because Andrei is has good idea. So consider subfamilies of n choose k to the power of wv. So you could hope that this guy can be naturally embedded into the p-biased Boolean cube just like k over n. But it is not true because the measure of f in the p-biased Boolean cube is roughly, it's at least the measure of f in the domain wn choose wk. And this could be much smaller than the measure of f in the initial domain. So the naive embedding into the p-biased Boolean cube doesn't work. You need to do something else than working with families in like some w-partite structures or something.
And for spread, so for spread things, this kind of embeddings would work.
Would work, but in
But-
some
but
regimes
in
it's,
some
it's not
regimes,
general.
yeah.
Work, so
But for let's say hypercontractivity.
activity you need to invent something because you need to do something which will be aligned with the structure of this domain.
Any other question? If not, let's thank the speaker again.